First, I'd like to thank the organizers for giving me the chance to speak at this meeting. I know the planning went on for a long time, so 2 years ago I was asked to come, and so I've been looking forward to this meeting for 2 years. I'm learning a lot from it. I'm a quantum physicist, not a mathematician, so it's good for me to be here. I'm learning a lot of the math that I need to use. I hope that what I have to talk about here is clear, trying to make it as clear as possible. Anybody wants to interrupt me, please do so. I've learned at this meeting that nobody is shy about interrupting anyway, so I don't think that's going to be a problem. Okay, so I'd like to, I got to figure out pointer. Anybody know which button to push? Probably just, okay, great, thanks. Okay, so I'd like to talk to you about some work I've been doing. Patrick Hayden is in physics at Stanford University, and he's got 2 students, Sepper and Grant, that I've been working with. And then more recently in my group, Yadong, Abdullah, and Masood, and I are working on carrying this project a bit further. The origin of this particular niche area came from Adrian Kent at Oxford. He called it summoning quantum information, and then Patrick Hayden has tended to call it space-time replication. The short story is that we're interested in a relativistic version of no cloning. So one of the fundamental principles of quantum mechanics that's proven simply by linearity is that one cannot perfectly clone a state. So I could take a piece of paper with writing on it, I could put it in a photocopy machine, and classically nothing prevents me in principle from being able to create a perfect copy of what's on the piece of paper in the photocopier. But quantum mechanically, we can't do so. We have ways around the no cloning, for example, teleportation, where we'll destroy a copy here and create a replica over there. And so in order to send that, to create the copy there, through quantum mechanics, it's required to destroy it over here. So we have ways of trying to get around it. But the purpose of this space-time replication is to marry 2 topics together. One is quantum mechanics no cloning principle, and the other is special relativity that says that information can't travel faster than the speed of light. So the concept to bear in mind as I go through is the following, that in a sense, when you take relativity, you think of space-time trajectory. So I'm standing here at the front. In a minute, I'm in some sense a copy of myself. So here I am, and a minute later, I'm a copy of myself. And so you can think of a trajectory in space-time as a sequence of copying. On the other hand, in a space-like way, I can't create a copy of myself exactly beside myself, so I'm forbidden to copy along space-like trajectories, but I'm allowed to copy along time-like trajectories. So the goal is to construct a space-time covariant way of knowing what's copyable and what isn't. The technique that I'm going to use is known as secret sharing. I don't know if there's any computer scientists or cryptographers here, but secret sharing is a cryptographic protocol that's used for online auctions, online voting in the Clinton era, not Hillary but Bill. There was also a proposal to have a Clipper chip, which was fortunately defeated, but the idea is that all cryptography would involve shares, and the government would have a share, so would have some control over it. So the technique that we're going to use in order to do a space-time covariant version of cloning is to use the secret sharing protocol. So I need to get all that across. It's related here because I'm going to be using the coherent states, the Heisenberg-Weil-Heisenberg type coherent states. Okay, I'm at the University of Calgary. I'm also appointed at the University of Science and Technology of China. I don't think anybody here except me can read that. So this is a university I'm at 10 weeks a year. I'm currently on sabbatical at Caltech. Also, New Journal of Physics, if anybody wants to talk about it, I'm the editor-in-chief, so I'm happy to propagandize for it, but not to give any discounts. Author pays, so if you're asking me about a discount, don't ask. And I'm also a senior fellow for the Canadian Institute for Advanced Research, and these are the funding agencies that have been help supporting the work. Actually, there's more, I should have put more in. Okay, so here's the motivation. I told you at the beginning, the idea is to generalize no cloning to a relativistic setting. That's essentially done by Adrian Kant, developed further by Patrick Hayden with his former student Alex May, and then his group at Stanford, and then we're working on it. So it's a very small community working on this problem at the moment. And the idea is that we're finding that we use the secret sharing protocol, which we deal with quantum mechanically. This is the underlying cryptographic protocol for the state replication. So we're finding that we can make relativistic cloning principles by using secret sharing. One of the advances I'm trying to work on, and I'll talk a bit about it, is to turn it into a game. So now there's a community of young people who play games and they take something and they turn it into a game like a movie, and there's now even a word called gamify. So we're gamifying this, where we're looking at aspects of resources required where somebody can prove they can clone even though it's physically impossible, and it just comes to limited resources. Mathematically, this comes in because I'll be using unnormalizable operators. We'll be encoding in position and momentum, and I'm sure most of you know better than I do the mathematical issues that arise. So if you assume perfect position preparation and perfect position measurement, you run into problems mathematically, and they result in resource limitations, and we're trying to consider those in the framework of game theory. And then finally, this is the continuous variable, the idea of using position states as a basis. So we're using that, but it turns out that in order to make use, to recognize the limitations of these unnormalizable operators, we have to use what's known as a ramp secret sharing scheme. So in secret sharing, the idea is that I send out information to you in the audience in a way that only subsets that I allow can reconstruct, and subsets that I deny don't reconstruct. This is relevant when we get to space-time trajectories because the allowed ones exist in are time-like connected, and the disallowed ones are space-like connected. But because of the mathematics of continuous variables, we have to use what's called ramp secret sharing. This is a fairly recent cryptographic protocol, and it allows leakage. So the question that comes up in ramp secret sharing is what happens if information leaks? And when you're dealing with Gaussian states, there's necessarily leakage. And so the ramp secret sharing gives us a framework for dealing with it. So these are all the motivations of the project, and I'll see how far I get in the remaining time. And I'm happy for interruptions, and I'm okay with not getting to the end. So anybody wants to raise things, it's fine. Okay, here's the context for it. And so I'm sorry to say, I know it's a math-oriented meeting. I'm kind of a cartoon guy, so most things will be cartoons, because that's how I think. So I hope you don't mind if I'm doing that, and I'm happy to discuss the math. What we have here, this is a box that represents the universe, and these are going to be space-time regions. Now, let me explain. What's going to happen here is there are two languages I'm going to use. One is the secret sharing language, and the other is the game or computer science type language. So over here we have a dealer and a referee. And the dealer and the referee together become what's called a verifier in theoretical computer science. And the player is going to receive a state. Now it could be a pure state tensored with the rest of the universe, or it could be entangled with something else. So the dealer is going to send a state to a player, and then the player is going to deliver the state to a referee at the end in such a way that the referee can tell the dealer late where to deliver it. So in our way of, and this is the Adrian Kant summoning idea, in the way of trying to generalize the no cloning principle, the idea is that this is like a black box, and the testing of the cloning principle is to say there are certain points that the referee is going to demand the state appear. And the configuration within there is going to be the space-time configuration, or the trajectories are going to be set up so if the referee doesn't know about secret sharing, the referee will say, oh, that's impossible to produce the state at any of those points that I decide later unless it's violating a no cloning principle. Of course, a smart referee will know everything and realize how the trick is being done. So the idea of operationalizing it is to say, so if I take the no cloning principle and I say to you I can clone, you can say, well, if you can clone, here are 2 points that are dislocated, they're space-like separated. I'm not going to tell you which one, but I might want to see it here or I might want to see it here, and you have to deliver, and I'll tell you which one to deliver at when it's too late to communicate between the two. So that's the way of operationalizing. If you don't get that, ask me now. Okay, so I'll keep going. Then, so the dealer and the referee form a team that's the verifier, and over here, these are the regions. So here you see 2 cones. So the idea is that the cone tells you whether, so if you start off here, this would be a point. All points in the red cone correspond to points that are time-like accessible by a person here. So a person here can send information at any point in the cone and not outside, and the boundary of the cone is the light-like curves, so they're the limitation to communication based on the speed of light. And the blue cone is the past. So this is the future of this point. This is the past of this point. And this one can receive messages from any point in the blue cone, but not outside. Yes?
Doing that, you suppose there is a consistent localization in quantum relativistic mechanics.
Yeah, you're asking about like a compact support.
I mean, really, localization operator has to exist and has to be consistent with relativity, space-time relativity. So you assume you define well localization within the framework of quantum theory and special relativity.
Yeah, so if your question is, like, I think what you're doing is anticipating when I get to coherent states. No, but is that right? You're thinking about that. And then in that case, so what the question is whether there's a way of consistently localizing in a relativistic fashion to avoid that. And I think the answer is yes, but it hasn't been worked out. So I mentioned previously about using ramp secret sharing, and the ramp secret sharing takes into account leakage. If there's a way to develop a basis that's compact, localized to light cones, then it could be, but we haven't done anything like that.
It could be in contradiction with the Hegerfeld theorem of spreading of your, for instance, wave function. As soon as you have localized at a certain point of space-time, immediately you have a spreading beyond the light cone.
Right. Yeah, okay, no, these are good points. As I said, this niche area is still, it's in the baby stages, so there's a lot of problems, and this is an excellent one that need to be addressed. Okay, so here you can see it's color-coded. The player is in this region, the dealer, the referee. The reveal and request work like this. So the dealer sends a state that could be entangled or not with the rest of, with other modes, sends it, and then the player, the way the game works is that the player sends, could send the state to any beginning of the intersection of the future and past light cones. And this purple line, by the way, is the extreme case where the two light cones intersect only on a light-like curve. So these are all intersections of light cones. And then the referee says, show me the state at the endpoint of the red light cone, or endpoint of this light cone. And so these are known as reveal points, where the dealer sends it to the beginning. The request point is at the end of the pair of intersecting light cones. In this slide, the arrow is a quantum channel, and the black line is a classical channel. So there's a quantum channel to allow delivery of the state, quantum channels here, but this dealer then will send information here and say, we want it revealed here, but send it in. When that information comes, it's too late for the player to be able to connect with all possible points, to be able to send the information to all possible points. So the way that it's going to work is if the player can't copy quantum information, so the player can't send the quantum information to here and here and here. So instead, what the player does is encodes it in a larger state. In secret sharing, these are known as shares. So there's an encoding with shares distributed at each point, and then a subset of these can communicate at the end to replicate. So this is the relativistic version, and it reduces to the no cloning principle in the non-relativistic framework. Okay, mathematically, the way that we think about it, so let me just explain a bit, that in quantum information we tend to deal with qubits, and there's a language. There's the Pauli group, and the Pauli group are just set up by tensor products of Pauli matrices, and then the Clifford group is the normalizer of the Pauli group. We're going to deal with what's called continuous variable quantum information. So here, the mathematics that we use is going to be the Heisenberg-Weil-Heisenberg. N refers to a number of modes. Turns out that I'm going to turn this into a graph, and N will be the number of edges in a complete graph. This is the symplectic group 2NR. Now here, and this is a semi-direct product. So here I've got the X and the P. So capital X, you can see, is simply the exponentiating of some S dot X hat. That's a vector of position operators, and we have N of those. And then P is simply the exponentiation of the P operator. And on the right-hand side, I have the symplectic stuff. And here, this is a squeezing operator. This is what's sometimes called a QND gate. 15 years ago, I called that a controlled sum, but QMD seems to have caught on. This has the X from mode J and the P from mode K. And this is a Fourier transform here, which is simply, well, simple. It's just, if you think of harmonic oscillators, it's the sum of harmonic oscillator Hamiltonians. So we're going to assume here that all operations, coding, decoding operations, transformations by the player, by the dealer, everything is drawn, everything is done as unitary representations from this semi-direct product. Let me do it in pictures to try to explain it. First of all, we're going to use a stabilizer. Now, I'm not assuming people here know what stabilizers are, so I'll tell you, when you do coding theory in engineering, or when the idea is that you want some representation of your states so that it's very easy to devise codes to correct things and spot errors. In this case, the way that we represent the states is in terms of capital B, capital X. So we're going to represent the state as tensor products of these kinds of operators. So then the idea is that the position state is an eigenstate of the capital X. The momentum state is an eigenstate of the capital P. So instead of writing those states, we're going to write the operators that do what's called stabilize the states. And you'll see where that becomes valuable. But the idea of this is to use, when you use this stabilizer representation, it's possible to use coding theory in a fairly trivial way. So if you read a coding textbook, you can map it over to this. Of course, this is where the key point comes in, and it's that these position and momentum states we can construct as a basis, but they're not really valid in using them simultaneously for preparing states and for measuring. So instead, we consider squeeze states, and I've represented that by an ellipse of the Wigner function for the state. And so we consider ellipses, and the fact that these are Gaussians leads to problems later on. So the compact support question is a very good one. And then we have these operations. So here I show you the QND and Fourier transform. Over here, let's say that our state was x1 and x2 going in. This allows any state because quantum mechanics is linear, so we can consider any state being any state subject to mathematical rules as being a superposition of those and those. And then the Fourier transform converts x1 to p1, the momentum state, where I put a tilde on to indicate a momentum state. The QND gate is this controlled sum, and the result turns out to be this. And I leave that as homework for you to show that. But that's one of the useful gates. We're going to convert the coding into circuits so that we can design experiments to be able to do it. But the circuits are an important way of representing what's going on. This is laid out in a paper I wrote 14 years ago with colleagues. Okay, now the idea is that we think of it as follows. We have the Heisenberg-Weil group, we have the symplectic, the semi-direct product. The stabilizers form a zero-measure subset of the set of operators that come from Heisenberg-Weil N. These are the errors that we can get. Now, errors could be generated by elements of the group, or they could be worse. They could be, say, in the enveloping algebra, so be worse outside. One of the dirty secrets in this field is we pretend these don't happen, but they do. But for this talk, I'm going to just assume they don't happen. And so all the errors that happen can be addressed by following what happens in the stabilizer group and writing code. So we code things, errors happen, and then we correct and decode. Errors in our case would be violating the laws of physics. So in the relativistic framework, somebody might grab, if somebody's able to cheat and communicate faster than the speed of light, that goes in the error framework. And the normalizer, this is the normalizer of the stabilizer group. It covers the zero measure set, and also there are normalizers that are outside the Heisenberg-Weil group. And so this just lays out a pathway for using error correction in a continuous variable framework. Okay, here's the way the replication game works then, is we combine the dealer and the referee, and then the dealer plus referee work as a team to be the verifier. And the verifier is testing whether the player, who works with agents at the request and reveal points, whether the player can prove, there are two questions. Can the player prove that she is, and there was a question about she before. So in quantum information, we try to have half the parties female, half male, because we're affirmative action. We're affirmative action subset of the community, so that's how it works.
Alice and Bob.
Alice and Bob, exactly. So yeah, if you want to know why I'm going to say she, it's because women make up over half the population.
It's a lot better to use it.
No, yeah, we don't, because for history, it's been he. It's not fair.
It's better because it's neutral.
No, but it's not better to me because I want to use she. I don't want to use it. Okay, then what we have is, so the player is, in this case, I'm going to say the player with the agents or the prover is she, he is the verifier. So what's going to happen is she has to prove that she can replicate to the limits of what physics allows, and she has to fail when the verifier is demanding that she send states that are outside of the bound of what's allowed by relativistic quantum mechanics. So here, this is representing it. So if the prover, if she succeeds in doing it, then the verifier will accept the answer with some probability. And if she fails, then the prover will reject with some probability. So in computer science, this is known as the completeness condition, that the verifier accepts with high probability if there's success, and the soundness condition is that the verifier will reject if there's a high probability, reject with high probability if the prover has failed. So this is the idea. And if that doesn't work, then either the laws of physics are different from what we thought, or the prover is stronger than the verifier assumes, which is cheating. Okay, now, there's a set of conditions that are established, and this leads to graph theory. The set of conditions for space-time replication, this is laid out in a paper by Hayden and May, published this year. These are causal diamonds, and then this is allowed. So there's a set of conditions on communication pathways between the different diamonds that says this will work, and there are conditions when it fails, and I'll explain in a moment. But what we're going to do is to turn these configurations into graphs, and it will turn out that it can fail if and only if the graph that we constructed is a directed complete graph. Okay, now in playing the game, there are different strategies. So in order to test whether space-time replication happens or not, the verifier can consider different approaches. I just show a couple here. One is the case where here's the prover, the verifier has an entangled state, sends one to the prover and demands that the prover reveal the state at any one of a set of points with a configuration that the verifier sets up that ensures that without secret sharing, this operation can't work. This can represent the basis state, and here, in this particular strategy, there's a joint measurement at the end, which corresponds to mixing these two beams, or these two states, at a beam splitter, so it's a rotation, it just does it xp plus px type rotation, and then measure that, and then if there's some probability, but if the result turns out to be 0 on the x and the p, both are 0, then the verifier accepts, and so the player has succeeded, prover succeeded, the player accepts. And because of the Gaussians, we wind up with probabilities, error probabilities of rejecting when they succeed, and vice versa. But the verifier has an infinite number of strategies. Another one is to use an entangled coherent state, and then subject it to number operations. So this is counting the number of particles in each beam, and have acceptance conditions that work very well. This kind of approach was laid out in a different context by Jung, Kim, and Lee 15 years ago. But the point is that in verifying, the verifier has different strategies to test whether replication happened. The prover also has different strategies to play the game. And here we can consider two cases. The prover is honest, or the prover is dishonest, trying to cheat. And the cheating comes up mathematically in the condition I mentioned here. So cheating comes up in the soundness condition. So in this case, we can consider honest prover. We think of code words. So the honest prover might use discrete variable. This is qubit-like code words. The continuous variable code word I'll talk about. Secret sharing and teleportation code, which is our new work that I'll tell you about depending on the time available. But the cheater can do other things. The cheater can say, well, if it's a single test, I'll gamble. I'll just send the state there and hope that that's where the verifier is going to ask me to reveal. So it's like it's playing a lottery. You might win. If you win, you get rich. So there's the lottery approach. There's concepts known as partial cloning, where you can't perfectly clone, but you can either clone badly or you can clone in a probabilistic fashion. And there's other ones where you can start to measure, do some kind of tomography on the state, learn something about it, and send it forward. So there are very cheating strategies that come up, and the strategies are laid out. This is Hayden and May's paper, and my work with Hayden's group. We have a new Journal of Physics paper that came out this year. Okay, now I want to explain to you how the coding is done. So here, so remember, the cones intersect in some nice-looking way, but if they intersect just barely, only on the forward and the past light cone intersect only on the space-like curve, then every intersection can be just thought of as a line. So now, for ease in drawing and representing, these lines, Y4 to Z4, is a line that represents the causal diamond, the intersection of the two light cones. This is a request point and a reveal point. So the dealer can send the state here and demand that the state is reproduced or replicated here or here or here. So the blue Z circles are the reveal points, and the red Ys are the request points, and these are each causal diamonds. The black lines correspond to allowed quantum channels, so that a request point can send. So the request point Y2 at the base of the causal diamond number 2 could directly send a state to the reveal point of causal diamond 3 through a quantum channel. All the quantum channels are allowed as long as the line is not greater than 45 degrees. That's the relativistic limit. Okay, so this is the way we do it. The player and the referee agree on a configuration, and then in order to devise it, we turn it into a graph as follows. So 1 in a diamond represents this line from Y1 to Z1, right? There's a diamond, that's this. Y2 to Z2 is that diamond. So what we have in this particular setup is that every diamond can communicate with another diamond, but only in the future. So we have a directed graph. Each of the edges in the graph correspond to quantum channels, and it's set up so that it's a complete graph. There's an edge between any pair of vertices. And we can prove that a complete directed graph is a necessary condition in order for, a necessary and sufficient condition for the player to be able to replicate. So this complete directed graph is tied in with this relativistic cloning argument. Then, in secret sharing, we have what are called access and adversary structures. So the access structure, you can think of the power set of the set of all edges of the graph, and then the access structure is the subset of the power set where the coding is designed to allow replication. So in this element 1, we recognize that 1 has a quantum channel coming in, 2 channels coming out, So the access structure includes that particular case, this case with 2, this case with 3, 4, and so on, but it disallows cases where arrows did other things, and those are, so the adversary structure would be the set of all elements that aren't of this type, and they're denied by relativistic principles. So we construct an access structure. This is important because in secret sharing, you construct this access and adversary structure, and then there's a coding theory that we can make use of. Okay, and then once we set that up, we have to, the dealer is then going to send a state to the request agents that are going to be able to send it to the reveal agents. It turns out that when the dealer sends the state has to be partitioned into a number of shares. The shares are not the number of diamonds, but the number of edges in the graph. So here you see 6 edges, and in the 6 edges, in this particular configuration, they figure out that, that the request agent on diamond 2 has to get 2 shares. This one gets 2, 1, and 1. So there are 6 shares of the state. So you take a state, you encode it into, you have a 6-fold Hilbert space, you encode into that, and then transmit around. And then in this particular configuration, where the reveal point is 2. So after they're delivered, the referee says, show me the state at the end of diamond 2. They've done it so that 3 shares wind up here, 2 here, 1 here, and the coding is done so that any agent holding 3 shares, no, sorry, I shouldn't say that. Yeah, any agent holding these 3 shares is able to replicate the state. So that agent then has a decoding process that will turn these shares into a copy of the original and 2 garbage shares. So this is the procedure that we make use of. And in order to construct the code, we recognize that we can form a vector space out of these particular configurations. So here, this is the graph. This is a graph corresponding to 1, 2, 3. And then what we have here, we can consider like the 4 causal diamonds, and then we consider a basis set. And the basis set corresponds to directed loops. I should tell you that this is known as homological coding. So the concept of homological coding is that you make use of graph theory and then the topology of the graphs in order to construct the codes. So in these homological codes, it turns out that any configuration, when we have 4 diamonds, can be broken up into a set of triangular loops. So larger loops can be written as a sum of other loops. And we have stars. So these are star topologies. And we're able to then consider any configuration, any graph, as being a sum of diamonds and stars. We use a particular representation. There are 6 elements here, so they correspond to all 6 possible edges. The zeros say an edge doesn't exist. The 1s or -1s tell us an edge exists, and the plus or minus tells us which direction the arrow is. And then we're able to construct, we're able to use these vectors as a way of representing how to build up the graph. So any graph can be written as a sum of these 6-dimensional vectors. And then what we wind up doing here is we have to then use this particular coding to be able to write what's going on in the state. So these become representations of the stabilizers. Remember I had stabilizers over here. These things. So we have S and T. So I'm going to show you how to construct them. So we're going to use this graph decomposition to be able to write these S's and T's, and they will be in the operators. And so the graph decomposition will tell us what set of operators we want to write, and then they'll tell us a product of position and momentum states for different modes that we're going to use for our coding and decoding. So here, that's what we're doing here, is we're building up to write those stabilizer operators, and then it turns out that we just do a direct sum. So we have the vector space for the triangles, a vector space for the stars, and we do a direct sum. We have a second direct sum. The S's are going to live in here. The T's are going to be in this part. So you can think of a 12 by 12 matrix with 4 3 by 3 blocks. These are zeros. we have S's here, T's here. There's reasons for it. I don't have time at all to go into coding theory to explain. But it turns out that the reason that we have 2 0 blocks comes because we have to make sure our X's and P's commute. So we'll have, we'll construct our X's from a 3-dimensional space, our P's from a 3-dimensional space. We need 12 dimensions corresponding to the 6 modes so that we have this commuting condition. And this X of S's, you know, if we have S as a 6-dimensional vector, so it's a product of X's over 6 dimensions. The states that are eigenstates of the X of S's and the P of T's are going to be the states that we're going to look at coding and decoding. Yep.
You have, I think, by with the 6 spatial degrees, space degrees of freedom, you should have R13 there, no?
No, we're using, sorry?
It should be R13.
Well, we have 3, 3, 3, 3. So it adds to 12. Okay. Okay. All right. So this is the way it works. We construct the stabilizer. We use coding theory to do it. I don't have time to go into it, although I can talk about it privately with anybody. So these X, we construct a code for that particular directed complete graph that I showed you through some math that I don't present here. We have our S's and our T's. We want to encode one mode into 6. So a principle of coding theory then tells us we only need 5 modes to do it. So we have a vector space of dimension 5. And this is what we do. We write the X's in that fashion, and then we can consider our coded state. So once we write that, we can consider this as our basis set. We work in this basis. If you see, like, no integral, the state X is an eigenstate of X of S, so capital X. But if we have the capital P, then it's simply the Fourier transform. The P state, like if you wrote integral of dy and then just the Y state, that would be the momentum state for the Y degree of freedom. So once we write this, we know exactly how to write that. And we can just take the operators and establish it. I don't have time to go through them all, but here I just take the S23 case, and then I show you that with the S23 case, with the 1 minus 1 and 1 here, the 1 gives us an X4, so we have X1 minus X2 plus X4, so the encoded state is then the eigenstate of these 3 operators. So we can read off here and know how to construct those states. If we could prepare such a state perfectly, then this is the way that we construct position and momentum states for the player to play the game.
So does it make sense to introduce some complex phases into those matrices?
Yeah, so you're saying, you mean because X of S, the X state won't be a +1 eigenstate, it'll be e to the I phase. Yeah, that's all accounted for. So when we do it and we go through the phases, in the end you have to take into account whether the phase will matter. But for the encoding process, the phases don't matter. Okay, then we have the case here. So this is how to construct the shares. Here we have 1, 2, 3, 4, 5 shares is all we need. And we use that particular encoding. So when the player receives the state from the dealer, the player then partitions into 5 shares to be distributed. And this is the state. And so 1, 2, 3, 4, 5 tells exactly what these agents are going to receive. 3 minutes. Okay, thanks. All right, so I think then we're able to construct an encoding and decoding strategy. The next thing we do is construct circuits. So this is our QND gate, or controlled sum gate, and this is adding C, and then this tells us how to construct, how to write it in circuit notation. This is a nice way of doing it. We turn the codes into circuits. So we say, this is the beginning where the dealer sends the state X to the agents. One agent gets 2 shares, and the others get 1 share. Then, but before sending it, the player, before sending to the agent, will do an encoding. So this state will be Fourier transformed into a momentum state. This is position equals 0, it becomes a momentum state. Then there will be the controlled sum operation of this kind to yield a new state, and so on. Going through that process with only these 2 kinds of operations, then the first agent will get these two, and then the second, third, and fourth will get those shares, and then go through the secret sharing process. And at the end, the agent, let's say it's the agent at the end of the second diamond, has to reveal. That agent receives shares from two others, does a decoding process, reveals it, and then passes the game. So this is the way we do the coding and decoding. There's an optical implementation I'll skip because it's not a physics meeting. And then what's happened is in the work that was published this year, me and Patrick Hayden's group at Stanford, that one we just had ad hoc code. So we looked at it, we'd say given a particular structure, we would design how it's going to work, but it was just guesswork. And now we've managed to develop an algorithm. So given any direct complete graph of any size, we're now able to construct, we have an algorithm that will deliver the coding and decoding. So we can do every case in an algorithmic fashion. I don't have time to do it, so this is more of a commercial to say we did it. I have slides on it, and that shows, this basically builds up our algorithm. The key mathematical step we had to work out was every directed complete graph has at least one acyclic subgraph. So we search for an acyclic subgraph, break it up, and then in this case we found two acyclic subgraphs, and then we have a remainder, and then we break that up, and we always break it up into three shares. So we then have a subgraph, and when we do it, we're able to then do our encoding and decoding. Here we then do the ramp secret sharing. So the ramp secret sharing is the one that we use because instead of using position states, we use Gaussian states. And Gaussian states have leakage, and the leakage arises in the mutual information that we calculate. So in secret sharing, security is based on mutual information. And we analyze our resources and consider how to construct things and compare. And so these are just resource analysis that I won't go into. So I think I'll stop here to hear questions. Thanks.
This is on the theoretical level. How do you prepare? So concerning because when you start with well-localized states, x 0, 0, 0, so you think to some experimental device in order to prepare those states in a precise localization, and afterwards you have another device which is going to perform the Fourier transform and so on. It is something which is at the moment experimentally implemented?
Yeah, okay, good question. So you're asking me a physics question.
Yeah.
So this, in the experimental implementation that we have in mind, this is the coherent state I've written as alpha. These are vacuum states, so it's amplitude zero coherent states. OPO stands for optical parametric oscillator. And so these would create entangled states. So this becomes, or a two-mode squeeze state, if you like. Squeeze state over 2 degrees of freedom. This BS stands for beam splitter, and the beam splitter can have phases in it. So we have pi on 2 or minus pi on 2. So these are coded half-silvered mirrors. And then we have a structure for doing this. All these things are perfectly feasible now.
Yes, but my question was for the previous diagram when you start, yes, when we start with X states, not with...
yeah, those are impossible. Those are impossible.
They are possible?
No.
No.
They are impossible. Yeah, so they're impossible, but I'm saying...
For understanding the background.
It's for understanding, but what I'm trying to convey in a more mathematical way is that we use it for understanding, but it is not they're impossible, but not just in a practical sense. We have mathematical reasons to say they're not proper states. So we have to regularize them in some way. So a whole theory, so if a theory is developed and has a technological challenge, it's okay. We don't, we can put aside the technology and be philosophical. But if a theory is based on this kind of state, then we have the problem that even on a theoretical level, it's not consistent. And then your question about the compact support version is exactly right. That's what should be done.
I have a bit more mathematical question regarding subgraphs of complete directed graphs, and you are encoding those subgraphs by vectors, and then you have this orthogonality relation between the subspaces. And my question is more mathematical. I mean, for subgraphs of, for complete directed graphs of arbitrary size, can you always construct such subgraphs with those properties, and what are those? I mean,
okay, good question. Well, the answer, I'm sure you know, is no. So the idea of this one, where we've got these triangular directed loops and stars, that decomposition only works for the direct complete graph with 4 vertices. And then, so the answer is no. That's why we've developed the new routine where we do this decomposition into, so we take this, our algorithm always decomposes it into 3 graphs, so the sum of the 3 makes this one, with at least one of them being acyclic. So first we prove there's always an acyclic subgraph, and then we always decompose to 3, and then in this case we have 2, and then we just decompose that one. In this case, so we decompose that one, we have acyclic. Acyclic just means, if it's cyclic, it's a loop. This is not a loop. And then we have, sometimes there's a smaller one, and this is easy to implement. Then what we do is count the number of edges after we fully decompose into 3 vertex acyclic and possibly a 2, and then or we can have directed, and then we have coding procedures developed in all the cases.
See, and then this works for graphs of arbitrary number of vertices. The procedure.
Complete graphs. Complete directed graphs of any size can be decomposed in this way.
Okay. Yes, thanks.
You are using here the Heisenberg group and the symplectic group.
Yes.
But have you think of using the Poincare group and coherent state of the Poincare group because you are in the relativistic setting?
Well, okay, I understand what you're saying. So we're using this semi-direct product because all we're considering is how to do the coding. So the Poincare group makes sense if we're talking about the physics going on in space-time between the agents, which that arises in the sense that we're going to describe what's possible, what's impossible, and that should be used. What happens here is once we go to these graphs, we've already finished with using the Poincare group. So when we set up these causal diamonds and the communication between them, the Poincare group is used to that stage. And then at this stage, the trick is, given this complete directed graph representing the communication links, how do we then do the encoding? And then the Heisenberg-Weil semi-direct product with symplectic comes into play. But what you're asking is important. We could then ask the question, there's other questions that could come up. What happens in curved space-time, for example? What happens in accelerating frames? Which goes, so there are different questions that come up. And then going from this to deciding how things are connected would then require analyzing curved space-time or whatever we needed to do. Yeah, quantum field theory, yeah.
We need to stop here, so let's thank Barry.